All right, today we're going to jump into something really cool called GenosDB. We're going to break down how it cracks a super tough nut, making real-time, collaborative apps, think Google Docs, work without needing a central server keeping everything in line. Let's get into it. So have you ever really thought about that? When you and a bunch of colleagues are all in a dock typing away at the same time, there's usually this big, powerful server in the cloud playing traffic cop. But what if? What if you could get that same seamless experience, but completely peer-to-peer? No central server at all. Well, that is the huge engineering puzzle that GenosDB was built to solve. So here's our game plan. We'll kick things off with the big picture serverless data problem. Then we'll see how GenosDB magically keeps everyone's data in sync. After that, we'll dive into its zero-trust security model, figure out how it stops edit wars, and then finally, we'll pull it all together to see how this whole resilient system works. Okay, let's set the stage here. In pretty much every app you use today, there's a central server that is the ultimate source of truth. It has the final say. But in the world GenosDB creates, a peer-to-peer network, every single user is their own server. Just think about that. It creates this Wild West environment where there's no single boss to decide which version of the data is the right one. Okay, so that leads us to our first massive challenge, synchronization. Right? If you've got, say, 100 people all making little edits, how in the world do you keep everyone's screen showing the exact same thing without just melting the network? You can't just send the entire document to everyone every time someone types a single letter. That would be insane. It just wouldn't work. And this is where GenosDB gets really, really clever. It uses what it calls a hybrid sync engine. Now, the best way to think about this is like having two different gears. For people who are online and working, it uses Delta Sync. This is the fast lane. It just zips over the tiny little changes that have happened since you last checked in. Super efficient. But for someone who just logged on for the first time or who's been offline all weekend, it shifts gears to the full state fallback. That's the safety net. It sends them the entire, complete, up-to-date data set. This way you get the best of both worlds, lightning speed for active users and bulletproof reliability for everyone else. So let's take a closer look at that fast lane, the Delta Sync. It's basically a 5-step process. First, anytime you do anything, it gets logged on your local machine in an oplog. Then, when you connect to another user, your computer basically says, hey, the last thing I saw from you was at this timestamp. What have you got for me since then? Their machine quickly figures out the difference, the delta, bundles up just those few new changes, compresses them, and shoots them over. Your machine applies that tiny little update, and boom, you're instantly caught up. It's incredibly elegant. Okay, so we're all in sync. Awesome. But wait, this opens up a whole new can of worms, doesn't it? In this serverless world, you're getting data updates directly from other people's computers, not some trusted company's server. How can you be sure the data isn't fake, or that someone isn't trying to hijack the whole document? GenosDB's answer to this is a powerful security philosophy called zero trust, and it is exactly what it sounds like. You trust no one. By default, every single bit of data coming from anyone else is assumed to be hostile until it's proven to be legitimate. This means every single person's computer in the network acts as its own security guard, its own bouncer. So how on earth do you enforce that? Well, it's a really smart, layered system. First off, your identity isn't a simple username and password. It's a cryptographically secure Ethereum wallet that only you have the key to. Second, every single change you make, every character you type, is digitally signed by your private key before it even leaves your machine. Third, and this is the brilliant part, permissions, like who's an admin and who's just a viewer, aren't on some central server. They're actually part of the database that everyone has a copy of. And finally, when your sign change arrives, every peer verifies it all from scratch before they'll even consider accepting it. Think of it like a 4-step security gauntlet that every single update has to run. First, is the digital signature legit? Does it actually come from who it says it comes from? If not, it's tossed. Second, my computer looks at its local copy of the data and asks, okay, what permissions does this user have? Third, based on those permissions, are they even allowed to make this specific change? And fourth, if any of those checks fail, the update is just silently ignored. It gets dropped on the floor and never even gets close to your data. It's an incredibly robust design. All right, so we're in sync and we're secure. But now for the next classic problem in distributed systems. What happens when two people try to edit the exact same word at the exact same millisecond? Who wins? Without a central server to be the referee, how do you prevent chaos? How do you win the edit war? The secret sauce here is a very clever piece of tech called a hybrid logical clock, or HLC. Every single change gets a special timestamp. Now this timestamp has two parts. The first part is the physical component. That's just the normal time from the clock on the wall. It answers the question, roughly when did this happen? But the second part, the logical component, is a tiny little counter that ticks up with every action. This is the tiebreaker. It answers the crucial question, which one truly happened first? And it all comes down to this one simple, unbreakable rule that every computer follows independently. Last write wins. When there's a conflict, the timestamp with the later wall clock time wins, period. And if, by some miracle, they happen at the exact same millisecond, then the one with the higher logical counter wins. Because every single timestamp is unique. There is always a clear winner, and every single computer on the network will come to the exact same conclusion all on its own. Conflict over. Problem solved. So let's pull all these threads together. You've got this smart hybrid sync engine. You've got the paranoid zero-trust security model, and you've got this perfect tie-breaking clock system. Those are the three pillars. But there's one last piece of the puzzle, an unsung hero that makes the whole thing actually feel fast and smooth to you, the user. And that hero is the persistence worker. Basically, all the hard work of actually writing data to your hard drive happens in the background on a separate thread. This is huge because it means the user interface, the part you're clicking and typing on, never ever freezes, no matter how much data is being saved. It automatically uses the fastest storage technology your browser has, and it has a smart queue system to make sure nothing gets corrupted. It's the secret to making all of this complexity feel completely effortless. So when you put it all together, the syncing, the security, the conflict resolution, and the smooth performance, GenosDB offers a complete blueprint for building these new kinds of decentralized apps, which leaves us with a really exciting question to think about. If you no longer need a central server, what entirely new categories of private, resilient, local-first collaboration tools can we even begin to imagine?